Piyush, just one thing. Sorry, I'm pulling you back, but we did prove something last time, right? I mean, the fact that if every convex combination, not every, I mean, if every distribution over every product distribution is real rooted, then what was that theorem? Sorry.
So let's just check that. So what we showed is that if you have a bunch of polynomials, right? So you have this so-called product distribution over, like, so you have polynomials indexed by coordinates like S1 to Sn, where each Si is coming from some omega I. And then suppose that there's some distribution over some product distribution over this, all these SIs, over this omega is, for which the maximum root is at most gamma. And for every product distribution, the expected polynomial is real rooted. Then there is one setting of all the SIs for which the maximum root is at most gamma.
And so this we prove. Right?
So now, so in particular with something like this, if you show this, so this is trying to satisfy the second condition of that that lemma, right? So we are trying to show that a certain kind of so there are certain polynomials, so that under every product distribution the expectation is real rooted.
Right.
Yeah. So that's what.
Now I remember. Sorry.
Okay. So we started off with some simple exercise over determinants. The first one was to just a simple expansion, that if you look at the characteristic polynomial of any matrix M, you can expand. If you expand it out in powers of x, then the corresponding coefficients up to sign are just the kth minus. So the coefficient of x to the n minus k is just minus 1 to the power k. The kth minus, the sum of all the kth minors of M. So what is that? So you just go over all submatrices of M of size k cross k, like all square submatrices, symmetric. So you take the same rows and the same columns. So you just go over all such subsets and take the corresponding determinant, and you sum them up over all such sets. That's the coefficient of x to the n minus k. That is a simple proof. Okay. So one more thing we'll need, and this again, so I said that one thing to do would be to just look at the proof for the matrix tree theorem. So many of the calculations are going to look very similar. So that's what. So we'll do a second exercise, which will maybe again recall the calculations we did in the previous when we were looking at the matrix tree theorem. So suppose that u1, u2, un, um, and w1, w2, wn are vectors in C to the n. So all of them are in the same set, C to the n. So then, so one simple thing is that this outer product that we have been talking about, it has some simple description, right? It's exactly this. So if I look at a matrix where the columns are the UIs, so what is the dimension of this matrix?
N cross M.
Yeah, so it's n rows. So this is n cross n.
Sorry, UIs are column vectors, right?
Yeah. So all.
Yeah. But you have to multiply these by, so the UIs therefore get multiplied by the WIs corresponding.
Yeah.
Oh, okay. Yeah. Sure. Yeah.
Okay. So notice that the entries are not like that. So if you look at the ijth entry, that's not like the ijth entry is something very simple, some simple description of like just taking corresponding vector UI and multiplying. But that for that you have to take the rows of this first matrix and the columns of the second matrix. It's a bit weird, but this is still true, right? And it's easy to check. Okay. So then what I want to do is, what is this?
Sorry, what did you say was not true? This is true, right?
This is true, but suppose I want to look at some particular entry of this matrix. So this is a matrix, right, on the left hand side. If I want to look at the ijth entry, what is that? That is like I take the ith row of the matrix on the left and the jth column of the matrix on the right and multiply.
Yeah.
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 So that does not correspond to the UIs and WS. It's just a trivial fact.
Yeah. Because you are taking the linear combination of these things.
Yeah. Okay, so now let's do one more thing. So our interest is in all these minors, right? So what we want to understand is so then we want to say that and the sigma k of this I going from 1 to m ui wi star is exactly the sum over all t which
Sorry,
are
what was sigma k again, Piyush?
so sigma k. So remember, so sigma k is the sum of all minors. So sigma k of m is you go over all subsets of size k and you look at the rows and columns from S and take the determinant and then sum it.
Correct.
So it's t. So all k elements subsets of n. Right? N is not this is n, not m. N is the number, the dimension of each of the UIs. And then I take the determinant here of I in u by t w by t, where UIT is a t-dimensional vector. So in the obtained in the obvious way, right? So t-dimensional vector obtained by restricting the coordinates. Test it as determined. I mean, yes. So this. Yeah. So what have we done? So sigma k was like, so it was supposed to be the k cross k minor of a matrix, right? So each subset was supposed to be a determinant.
So something happened to you. I think I dropped out or something. Or did you drop out? I don't know.
No, I think it's fine.
Okay, just one second.
So,
okay.
So now the sigma k, yeah. So we have to now understand, like, yeah. So this, let's just prove it. I mean, yeah. So this is just expressing it again as a sum. So determinant of a sum, but now the sum is of some slightly smaller vectors. So in particular, suppose that what if somehow k was equal to m? So if k is equal to m, right? So each t is of size exactly m, right? There are m vectors, and you also have each vector is also of size m. Then, so sigma m, I going from 1 to m. So this, of course, implies that can only happen. This is a very special thing, right? Can only happen if m and k and n are all equal. But let me, but if they are equal, then this would be equal to
n has to be greater than equal to m, no?
Yeah. But the point is that this has now this special thing that if I multiply things out here, so this is again something that happened in the matrix tree theorem proof also. Then this just comes out. I mean, this doesn't, you don't need the previous thing to do this, but yeah, sigma k of just summation. So is not also that. If k equal to, then this is true. This zi is just come out. Why is that? just think of the definition of summation ui wi. So if I'm multiplying each zi by wi, that's like multiplying every column by zi. Now, if n and m are equal, that's what this k equal to m setting will, under this setup would imply. So if everything is equal, so these are both square matrices. So what is happening really is that I'm putting a diagonal matrix here, n cross n, and with the zi's on the in there, zi's on the diagonal. So the determinant of this whole thing, there'll be only one left. The determinant of this whole thing would be just the zi times the determinant. Like, so you just said that, I mean, the determinant is multiplicative. So the determinant of the diagonal matrix will just factor it. So you will get the usual thing times zi. So in the special case, you have this. But yeah, so this is just something to keep in mind. So whenever you can do this, you have this. This is a simple fact. This we will need to prove. So why is this true? So what is the definition? So the proof of so this star. So we just use the definition. So sigma k. So define, let us call m to be this capital M to be I, UI, W, I star. So then sigma k of m is by definition summation is subset of k and determinant of.
Sorry, Piyush, what are we proving? I mean,
this thing here.
Okay. But I thought that was, that's not obvious. Okay.
Well, let's see. So yeah, I mean it is. Yeah. So yeah, it's not complicated certainly. Yeah. So the point is, what is this MSS, and that is exactly what this is. So if I'm looking, yeah. So the whole point is this is exact. So note that. This is exactly UI as WI as star. So that's why it's because I was saying it is obvious. I goes from 1 to yeah. So and this is easy to see, right? Because what you're doing is taking this matrix M, taking the corresponding rows of S and the columns of this. So in the part that corresponds to just taking the rows of the left matrix, corresponding columns of the right matrix, and that's exactly what this UID WI star is. So the proof of star is also simple. So star forms. So this was the simpler part of the matrix tree theorem calculations we did. And one of the things that we use in, so the third one, which is not an exercise, but there's something to recall, is this Cauchy-Binet formula. Maybe we won't need it now, so let me just mention it later. Okay, so the third thing, so instead of Cauchy-Binet, let me just write something more complicated. So the third thing we'll need is a determinant identity, which will combine some of the things we have. Which is the following. So let W1 all the way to Wm be rank 1 matrices. So in particular, that means that there exists UI Vi such that each Wi is equal to UI Vi. I should be using dagger, whatever. This is conjugate transpose. Okay? So that's what rank 1 be. I mean, any rank 1 matrix has that kind of description. And then this characteristic polynomial of wi, which is determinant of a summation wi, it's a summation of is equal to I going from 0 to n x to the n minus k, and then S subset of n by k z to the s, which means the product. Yes, this is the product of zi I and times sigma k of a matrix of the sum of only those wi's which are in S. Okay, so notice that each this matrix is still n cross n, but now you are summing up over only k size. So you're only summing k of the matrices.
No, but Piyush, how did Z appear? What is Z on the right?
Oh, sorry. So this is Z here. So, yeah, so the Z will be important. So I'm looking at it. So Z's are just variables.
Okay.
Okay, so let's so maybe let's for now just assume this identity and then prove the theorem, and then we'll come back to the idea. So
this proof would be very similar to what you did last time, right? Exercise 1 or something.
Yeah, so it will basically be a combination of exercise 1, 2, and 2. That's the thing. So maybe yeah, that's the whole point of this. So maybe let's do this for now because we've already just seen this. Okay. So yeah, sorry. So and this also I missed. So maybe let me not do it for characteristic polynomial. Maybe so just to avoid tracking signs, let me do it with plus, and then with the minus it's easy, right? You just have to put a minus 1 to the power corresponding thing. So okay, so let's just prove this first. Okay, so this implies that characteristic polynomial of summation zi wi going from 1 to n, which is that of xi minus summation I going from 1 to m zi wi is exactly I going from 0 to n x to the power n minus k minus 1 to the power k. Some S subset. So S is an element of subset. This is an element of, is a k element subset of n. Product zi sigma k. So why the minus 1 to the power k?
Well, you absorb the minus into minus zi, right? And then
yeah, that's one. Yeah, that's simple. Yeah. Okay, so right. So now let's prove this identity. So proof of this 3. So so we are looking at this state of this, or rather this is equivalent. So so actually, yeah, so let me just prove this one. So this now suppose because it'll be easier to do with what you have done already. So zi wi. So now this is n. So now we have this our exercise 1 at our disposal. which expands out in powers of x. So because you want to expand powers of x, that maybe is relevant. So let's do that and see what happens. So then this is equal to I goes from 0 to n, x to the n minus k minus 1 to the power k, and then what? Sigma k of the matrix, right? So what is that? Sigma k of so now you have to understand what this sigma k of zi wi looks like. Okay, right? Sorry.
Yes.
Yeah. So now, okay. So now remember that we had this representation. So we call that wi is a rank one. That's the crucial thing. So these wi matrices are like ui vi dagger, where ui vi are in CPT. So now the sigma k I going from 1 to m zi ui vi star is what? So so we just so the zi wi I can just think of as one vector because zi is just a scalar and vi star is the other vector. So now let's just look at this second our second exercise. So that was exactly of this form, right? So we were trying to do sigma k of the sum, and then we expanded it over these determinants of these minors which were smaller. Right? So let's just put this is t in n k, and so the determinant of summation is zi ui t vi it should be, yeah, okay. So this is conjugate transpose. Usually it's a dagger, so sorry that I used that. Okay. So far so good, but there's still some of m things. Although this, so what is the setup now? So what is this matrix? So let's call this MT or something else. Let's call it KT. So this KT looks like this. So you have this K cross M matrix here, okay, and M cross K matrix here. What are the rows here? So the rows of this thing, the ith thing is Zi times UIT, and the ith thing here is just Vi T star, and because T is of size K, that's why these are these dimensions. And we are looking at a determinant of these things. Okay, and this is where we now recall our Cauchy-Binet formula that we have seen earlier. Which says that the determinant of A times B, so let A be K cross N, B M cross K, then determinant of A times B is exactly you go at all subsets of size K. So you just choose the corresponding columns, K columns of the left matrix. Look at that determinant. The determinant of the matrix, submatrix obtained by choosing the columns in S, and multiply that by the determinant of B obtained by choosing the corresponding rows of. So in this vector form, what does that tell us? So this determinant of kt, which is this determinant of I going from 1 to m of zi ui to that's what the determinant is. There's no sum here. So this looks like what? So this looks like if you just this is a sum over all subsets of A times the determinant of this. So, but this also, by the way, so this is also equal to the determinant is multiplicative, right? So I can also write it as the determinant of A, K, S, B. But that's exactly like I just chose only those only those columns. So this A, K, S, B, S, K is exactly, I chose only those columns of the columns of this left-hand matrix which correspond to S, and the rows of the right-hand matrix that correspond to S. And that is exactly, so this product is exactly what?
I mean,
Determinant
the
of the
corresponding,
product.
the corresponding UK.
Determinant of the product.
Yes, so what
By
the sum of Zi, Ui, where I is in S. Kind
yes,
of.
exactly. So right, and now notice that what is now there is something interesting, right? So this now we are in this setup. This observation that we made, like the minor that we, so this or maybe even directly, the point is that this matrix that we are looking at, right? So these matrices, they're k cross k matrices, right? And there's a z. So now, so let's look at this matrix. So this looks like a k cross k matrix where the right where this ith column is like a zi times ui uit, and then there is another k cross k matrix where the ith, this one is vi t star. So if I'm looking at a determinant of such a matrix, what is that? I can also write this as product of zi minus det. And this is because this S is of size k and T is also of size k. So these zi's are because you're just multiplying columns, so this whole thing is equal to this matrix without the zi's times the diagonal times this, where D is a diagonal matrix with zi on the diagonal. Okay. So what have we? So just let's just substitute this in our previous thing. So we get that the sigma k of summation zi I goes from 1 to m, zi ui vs star is sum over all t, which are n size, k size subsets of n times and then sum over all s, which are k size subsets of m. Okay, and then product of zi I in s times the determinant of summation I in s uit vit star. Okay, which is like, now let's just change the order of summation. So s subset of s k size subset of m, product of I in s zi, and then you have all k side subsets of n of the determinant summation I in s uit vit star. But what is this? Let's recall again exercise 2. So this is equal to just sigma k of I in s ui vi star. Right? So this is see that. So, so sigma k of any sum of vector like these rank 1 matrices is obtained by summing over all k size subsets of the coordinates and then looking at the full sum, determines the full sum but restricted to those the outer product but restricted to those coordinates. This is exactly what's happening here. So now the role of 1 to m has been taken over by s, but we're still taking k size subsets of the coordinates and then doing this now. So that's exactly what this is. So this is equal to s. So the important thing to remember here is that the two kinds of subsets behave differently: the subsets of coordinates and the subsets of the vectors. But this is exactly WI by definition. So we are done. So we get that this determinant of xi minus summation zi wi is equal to sum k goes from 0 to n, x to the n minus k minus 1 to the power k s subset of k I in s sigma k solution w whenever w n cross n okay, so this proves this identity. Okay, so now let's so is this clear? So the proof of the identity was sort of not so complicated. So the only thing was this interchanging this thing between the subsets of coordinates and subsets of variables. The crucial thing now is that somehow we have been able to obtain these the point is that now this whole thing we have been able to obtain. So if I ask you the coefficient of any monomial in Zi, right? You can tell me like what is the like what is the coefficient of product of Zi I in S for a particular S is right there in it. So that somehow should help us, right? Because extracting monomials using these differential operators is some trick that we have seen before, right? And so maybe that's how it's going. That's the kind of thing that's going to help us. So notice also that the polynomial on the left hand side will certainly be real rooted if the wi's were symmetric and zi's are sort of any numbers, right? Because then it will be a symmetric matrix, and so so we are getting somewhere close. So now let's so that's
so what did you say about the real rootedness? 1 second, please. Can you just
so suppose wi's were symmetric and zi's are any real numbers, then the left hand side polynomial is real rooted, right?
Yeah.
Okay.
No, Zi is a real. What do you mean? The polynomial?
So then in X it's real rooted.
X is real. Yeah. Okay.
Yeah.
I see.
And also if Zi's are negative, wi's are PS. Yeah. So we have seen like determinants. We understand sort of the real stability properties quite well. So we have seen this old result also, that even the multivariate determinant polynomial, as long as all the, so if you take determinant of summation xi ai, where ai's are PSD, and plus you add a Hermitian term, that's still real stable. So that's one of the first real stability results we did. So now so we will look at that. So we'll see how we'll now let me now state the main lemma, which will
rank 1 here.
Sorry.
Sorry, I was asking, the rank 1 can be gotten rid of, right? We can always decompose wi further if needed.
Yeah, but the crucial thing is, no, the rank 1 can be gotten rid of, because the thing is, here you get all subsets of those matrices,
Yeah.
right? So that's
rank 1.
Yeah. So that will change. So the right hand side will also change. That's right. That's the point.
So
okay.
The M will change. Is that what you're saying?
Yeah, the M will change. I mean, depending upon how you decompose, what you get here will change. So I mean, so you have to first so there can be many rank 1 decompositions. You take some rank 1 decomposition, then you will get something different. So that's the point. How you assign variables also, that would matter. I mean, this equality will not be true. That's the point. Without a rank 1, you can get something out of it, but it will not be the same equality. It will depend upon the rank 1 decomposition. So it's not buying as much. Okay, so so now the main thing that we will prove is the following, and so the main lemma of using this inequality would be that consider the mixed characteristic setup we had earlier. Setup from before. So what was this? Omega 1, omega m are finite sets of vectors in C to the n, and mu1 and mu so I don't know what the notation I was using, mu1, right? mu1 to mu m are probability distributions on omega 1 omega n, respectively, and mu is the this is like the distribution of sampling independently from each for each coordinate from independent. Okay. So then what then? So let AI be the expectation of summation of what is the expectation of just vi dagger when vi is sample according to mu. So this is the definition. Then this expected characteristic polynomial of this matrix vi star I goes from 1 to m, where each these v1 to vm is sampled according to this broad distribution mu, is exactly so to apply this operator 1 minus the derivative with respect to zi. So this big operator is applied to a polynomial. What is it polynomial? The polynomial is det of xi plus summation zi ai. Okay, and then after that, so let me just, and then after all this, the z1, all these zi's are set to 0. Why is this good? So why is this good? To see that we'll need one more lemma, which is something we've not seen before, but it's easy to prove given what we know. Is that if f z1 to zn is real stable, then 1 minus del del I, yeah, second is also real stable. So far I've seen that taking derivatives retains real stability. What I'm saying now is that if you take the derivative and then subtract the derivative from the original polynomial, that is also real stable. Okay. So with this, now we would have done, so given these two lemmas, the proof would be done, right? Because why? This determinant xi plus summation zi ai, ai's are PSD. Why is ai PSD?
Each vi star is PSD.
Yeah, and you're taking expectations, so it's some weighted sum of PSD matrix, positive weighted sum. So each ai is PSD. So now this det xi plus zi ai is a polynomial in variables x to z, x and z1 to zn. This is a real stable polynomial. I apply all these derivative operators to it, these operators which preserve real stability. So this whole thing remains real stable. Then I set some variables to 0, to 0, and then again real stability is maintained. So now this whole thing, this left hand side is a polynomial in x, right, which is a expectation of determinant xi. It's a polynomial in x, is real stable, and it's a real stable polynomial in a single variable, so it has to be real rooted because the coefficients are real. Okay, so let's prove the note together the two lemmas establish that the polynomial is real root. Okay. So because yeah.
So Piyush, is there a version of this thing when you know the instead of vectors you had matrices from which you were sampling, or
yes, some of this will break. I don't know offhand.
okay.
Yeah.
All right.
Okay, so yeah, so together these two things will imply real effects. Okay, so yeah, and wait, with previous stability results we have seen. So this I will leave as an exercise, like how given all so I'll prove these two lemmas and then how that implies that this is stable. This is easy exercise. Okay, so now let's prove the second lemma first. The proof of second lemma, that is actually the easier one. So if you have read the Borsia-Brandon thing, you probably already have a proof. Because and that proof just depends upon the fact that the polynomial x plus y is real stable. In fact, so given Borsia and Brandon's theory, the stability of the polynomial x plus y implies that this operator 1 minus d by d zi is stability preserving. It's that powerful. So
Sorry, what is the Borsia-Brandon theory?
yeah, so we won't need it. I haven't specified, but I'm just saying that it's powerful enough that using that theorem, all you need to show is that the polynomial x plus y is real stable, which is an obvious kind of statement, and that implies using their theorem that that 1 minus del zi will also be a stability preserving operator. But I won't use that result. We'll just prove it by hand. Even by hand is not so difficult.
So here, this 1 minus dou by dou zi,
Yeah.
you can take anything like 1 plus dou by dou zi, everything will work, or
1 plus I think doesn't work. Yeah, 1 minus will work. 1 minus any positive thing will work. Yeah, 1 plus might fail. Yeah, 1 plus might fail. Yeah, we'll see. Yeah, we'll see what's happening.
this is just the change of the derivatives at the root of it.
Huh? Yeah, so we'll have to just so we can just prove it more or less directly, or apply Borsia-Brandon's theorem and so on. But let's try to just prove it directly. Yeah. Okay. So yeah. So how will we do this? So fix. So suppose f z1. So without loss of generality, I'll take I equal to 1. So take I equal to 1. Fix z2 to zm in the upper half plane. Then by the real stability of f, all roots of gz, which is just f, the first coordinate is a z and the second coordinates are all second to m are all fixed, are satisfy all roots, let's say omega of this satisfy in omega. What should they satisfy?
Is less than
Less than equal to 0.
Yeah. In fact, they should also satisfy less than 0, right? But yeah, let's just stay with this. This should also satisfy less than 0 because setting.
Sorry, Piyush, what is F? I am a bit lost.
So what is the second lemma? Second lemma was that if F is real stable, then 1 minus d by, so 1 minus.
That's what you're proving.
Yeah.
Okay. I'm sorry.
Yeah. So
Without loss of generality, take I equals to 1. This means.
I mean, why? I mean, I just calling that variable on which I'm applying the derivative 1. The first.
Oh,
variable.
okay. Sorry. I got confused with the die of the complex plane. Sorry.
Oh, yeah. Okay, so this is yeah, for every key. Okay, so now let's see. So G has something, and what is this? So what we have to look at is this. So consider. So what we have to show. We want to show that. So it's basically a univariate problem that Z prime that GZ minus G prime Z has no roots. So all we need to show is that it's arbitrary. No roots in the upper half plane. No matter, as long as for any. So you have to do this for any Z to Z. I mean, open up. Okay. Right. So now, okay. So good. So now consider
G prime is the derivative, right?
Yeah. Okay. So now let so all of this will be is essentially trivial. If you exactly do what you have to do and get this. So now let X be some arbitrary. So now let X be arbitrary. In the upper half plane. Right. Okay. And then Gx is not equal to 0. Right? And open up. So Gx minus G prime X equal to 0 if and only 1 minus G prime X over Gx equal to 0. Basically, I can define by. But what is this 1 minus? But would note that this im of G prime X over Gx is what? Is the im of summation 1 over X minus omega I goes from 1 to degree of G, where omega I are roots of G and hence satisfy.
Sorry, Piyush, I'm a bit confused. So in F, we assume the coefficients are the coefficient of the original polynomial could be complex numbers.
Yeah, I mean, so have I ever used that it's real? I mean, so far I'm just saying take k equal to 1, fix some arbitrary.
No, I was just wondering why is g of z not real rooted? Because you have assumed those things to be complex numbers, is it?
Yeah, no, yeah. Even if the coefficients of f were real, z2 to zm are complex numbers, right? So even then I could not have claimed that.
Oh, you have assumed z2 to zm to be complex.
Yeah, I have to, because I have to prove this, that I have to prove this relatives for all r. So I have to show that there are no roots in. So when all these z's are in the upper half plane, there are no zeros. Right. So yeah. So let's just go over this once. So we have this f. We are looking at 1 minus the derivative with respect to the first coordinate of f. So so now, okay, so suppose that it is not real stable, then there must be some z2 z1 z2 so on zm in the upper half plane where it vanishes. So let me just take such a thing and look at z2 to zm, forget about the first coordinate, and look at the univariate polynomial, and I want to get a contradiction. That's what we are doing. So that's why all we need to show that this gz minus g prime z has no roots in the upper half plane for any such.
Okay.
Yeah. Okay. And hence satisfy right to be less than 0. And by assumption, imaginary part of x is strictly positive. So im of 1 x minus wi is strictly less than 0 for every I. So that means that im of g prime x over gx is strictly less than 0 for every x in the open upper half plane. So 1 minus g prime x gx is not equal to 0. Okay, and so gx minus g prime x not equal to 0. Upper half plane. And which means that 1 minus del z1 of f z1 to zn is not equal to 0. Yeah. Or in the open upper half plane. Okay. So this kind of argument of just looking at, so this is the I mean the calculation might look a bit different, but the proof is actually very simple. Sorry, very similar to what we did for Gauss's lemma, Gauss-Lucas lemma. So yeah, so we just look at the roots and see how they're behaving. Yeah, but again, so so this looks like a sort of straightforward but long-winded calculation. And this Borsia-Brandon theorem, for example, would tell you that this follows from the fact that x plus y is real root. From that fact, it follows that 1 minus del z is a real stability. Yeah. So yeah, so it's a powerful kind of result. And okay, so now we have proved this. So is this clear? So this is sort of important. So although it's the easier part. So is this fine? Any questions about this? Okay, so now let's start proving the first one. So, which is also, we have done most of the hard work for it, which is to prove that this the expected characteristic polynomial is exactly this thing. So actually, let us start on the right hand side, and so now prove the main lemma. So let's look at this 1 minus del zi, I going from 1 to m det xi plus summation zi. So if I just expand this out, so if I take these derivative operations and then expand them out, so what do I get? I get summation over all subsets of m, right? Minus 1 to the power the size of s. And then I have this product of del zi I in s, right? Of this operator applied to determinant of xi summation zi. And then I have to, of course, set everything to. But let me ask, so what is this? This thing we have seen before, right? What you take a polynomial. So this is a polynomial. You take a polynomial, and then you apply a bunch of operators on it. So this derivatives on it, and then set all the variables to 0. What will survive? So what I'm asking is, what is this?
So the ones where all the coefficients, all the exponents are exactly 1.
Yeah, so the only thing that survives is exactly the coefficient of that term in the polynomial, in which the powers of the zi, which are in S, is exactly 1. So let's check that. So anything which has power of zi which is more than 1, why will that go away?
When you differentiate and substitute 0, it will become.
Yeah, so when you differentiate it, it still it retains at least 1 degree, and when you set to 0, it goes away. So anything that is bigger than 1 will go away. Okay, so whether you differentiate or not, it remains bigger than or equal to 1, and when it's set to 0, it goes away. Things where, what happens to things where it is less, so where say zi does not appear, those become,
when you differentiate.
Yeah, that vanishes when you differentiate. So the only things that do survive, and we have done it sometimes, a few times before, the only things that do survive are those where zi, the degree of these zi is exactly in it. So in particular, this is exactly the coefficient of zi. Yeah.
So here earlier we just showed that this product of 1 minus del by del zi, this thing preserves real stability. And we also know that this determinant is real stable.
Yeah.
So why are we already not done? Why are we expanding out the...
Well, because you have to prove the main lemma, right? So we have to prove that what we get is actually equal to what we wanted. So that this expression is equal to the characteristic polynomial. So what we want to prove is that this polynomial, the expected,
so it's
is
not
real.
the stability.
No. Yes, it's immediately clear from all we have shown before that this right-hand polynomial is real rooted. But we all now I want to show that this right-hand polynomial is exactly equal to the polynomial that we are interested in, which is the expected characteristic polynomial. This is not the polynomial we are interested in, right? But remember, what is the polynomial we are interested in? The polynomial we are interested in is this expected characteristic polynomial, where we have these vectors coming from distributions mean I, and then we take the characteristic polynomial of the rank 1 sum, and then we take the expectation overall over the distribution of the vectors. That's the polynomial we are interested in. The claim is that is equal to this thing we have defined. Sure, yeah.
So that is the main.
Yes, yeah. That is the main lemma, that they are interested in. So okay, so yeah, so the coefficient. So this is the coefficient of the product of zi in the determinant of summation xi plus zi pi. But this we know. This we sort of do we know this? or not? Or do we know how to compute this? Have you seen this polynomial before?
Yes, it is similar to the spanning tree polynomial.
No, maybe we have seen it even more recently. We have seen just today, right? This thing here.
Oh, okay.
But there is some issue. So we have seen
Minus
this.
x, sorry.
The minus is okay. So it almost looks the same. Determinant of xi plus zi summation zi wi, and the coefficient of zi is just sigma k of summation wi. But there's some problem, right? It relates to a question which Siddharth was asking earlier.
These matrices are not necessarily PSP.
No, so no way. Well, I mean, this is an even more general result. It works for all matrices, all rank 1 matrices, not just for PSD matrices. Here we even have PSD matrices. AIs are PSD.
In the last expression.
Sorry. Sorry. Yeah.
So AIs are AIs rank 1 matrices?
Yeah, are they? Yeah. So that's the question. So not in general, right? Because you're taking, so these VIs need not, I mean, like, in general, they won't be, right? This new I is not guaranteed to be supported on vectors that are in some linear subspace of dimension 1.
Yes.
So in general, the AIs are not rank 1. So earlier what we had is that for the crucial thing is for rank 1 matrices, determinant of xi plus summation I going from 1 to n zi yeah wi rank 1 matrix wi has this nice description. I goes from 0 to n x to the n minus k. So what was it? Let's yes. Product and then sigma k of summation. But we are not in rank. The AIs are not rank 1. Okay, but the AIs are not rank 1, but they are some of rank 1, right? So that's what Siddharth was saying. So AIs are not rank 1. But each AI has of the following form. What is the form? So each the vector, so there is some finite set, right? So there is some Li, which is the number of entries in omega I. And for this, they have, sorry, I should not call it. So this J, and this new I, the J thing, and for that I have this Vj, Vij, Vij stuff, where omega I is Vi1, Vi1, Vi2, so on to Vi. Is this fine?
Yes.
Yeah. So so each of them has this form, right? And the new I is a probability distribution.
So cannot any PSD matrix be written in this way?
Yes, but I mean the point is that these are I mean AI is also has a special thing. It's a probability distribution, or it's coming from this probability distribution. So we'll ultimately we want to get to these vectors also. So this is the one we have to use. Okay. Right. So now let's see. So therefore, this determinant of this polynomial that we are dealing with, ZI from 1 to n, it does expand out as summation I going from 1 to m, j going from 1 to li of zi times mu I j vi j vi j transpose. Right. And this now is a sum of rank 1 matrices, right? Which is equal to, by our identity, sum k goes from 0 to n, x to the n minus k. Then we have subsets. S is a subset of, oh, sorry, this was not a subset of m, it was a subset of this m by k. So let's just check this. So recall that in this thing, we have to, wait, what did I do? I missed something. So, yeah, this is m, it's not n. Oh, I've been writing this thing wrong for a long time. This is subset of the how many matrices there are. So yeah, so let's just make sure that we did this correctly. So so in the proof we did see this, right? So in the end, what happened was that you are left with the subsets are subsets of the set of vectors, the set of matrices, the rank 1 matrices that you. So now what is this set as a subset of? It's a subset of these tuples, right? So let me just call this subset something. Let me just call this k for now, and I'll just write down what k is. K2, not k, k is not a good thing. Let me just say, I don't know what's a good letter. So, let me just call it w. W, choose k of okay. So each element of S is a pair, right? And the variables that come. So how do I say? Yeah, so let me just write down. So the product of Z, so the first coordinate of S, which is which ranges over 1 to m, and then you also have the product of S in S of nu of the first coordinate of S at the second coordinate of S. And then you also have the sigma k of summation. So S is sort of like a pair. So that's now this one. So what is now this? So where W is the set of pairs I comma j, where 1 is less than I is less than what? M, and 1 is less than j is less than li. Given W in W, we write so given let's say, so each W each W in W is written as the pair W1 W1 W2. So 1 is less than W1 is less than M, and 1 is less than W2 is less than L of W1 for every W.
Is this double summation important in the sense of this structure? Can we not think of it as just a sum over arbitrary m times some li vector sum? Can I not think of it as a single sum and just work then?
Will it work? So the point is that we have to get to these vectors, right? So we have to, this has to be disentangled later on also. No? So you have to get to the expected characteristic polynomial, and there the vectors do appear separately.
Okay.
So yeah. So
I see.
yeah. Okay. So good. So now let's see. So now we are in sort of good shape. So now we have to just check coefficients. Okay. So what is the coefficient? So what is the coefficient? Of product zi I in T in that summation zi where T is an T is a subset of just n. So can you read it off from this expression? So which sets S can give rise to such a coefficient? That's the question.
From each of the
So first thing to notice is this thing is no more multilinear, right? So there are some non-multilinear coefficients also, but we are only interested in the multilinear ones, right? Those are the only ones that will appear in the final thing, because everything else is just gone. So right. So for a particular T that is a subset of M of size some K, right? Where can it come from? So it has to come from the particular K. The K has to be the same because the degree K terms come from exactly those sets which are of size. The degree is not changing. So yeah, they have to come from some S which is of size K. But as Siddharth was saying, the first coordinates must all be different. Okay. So these are and they must exactly be the what should they be? What should be the first coordinates? Exactly the elements of T. Right? So yeah. So this is exactly S subset of W K such that T is equal to S1 given and then you have this product of a new S1 of S2 SNS times sigma K of summation SNS new S and new star. But this is another way of writing it. Basically, what you have done is so these sets exactly correspond to functions from T to, so for each element of T, it's a function. You have to basically, for every entry in T, you have to choose a vector from the corresponding set, right? So do you see what I'm saying? So this is nothing but so let's say J1 with so how do I write this? So there is a So sum over all functions. So sum over all some let me just call them f's, where what you do is you just go over I in t and you look at a new I of fi, and then you have sigma k of summation again I in t, and you look at vi vi fi vi, where f is an assignment where f ranges over all assignments from 1 to li to each element I of t. Okay. Right. So this is the coefficient, and this all now starts almost looking like the thing, right? So what is this? This is the, so this thing is exactly the probability of choosing the vector vi in the on the tth coordinate. Is that clear?
No, I'm not able to see what
so just let's just look at it. So what is this new I? So now these, so what are these t's? So t's are these, so you have chosen some set of, so there were m random vectors, right? You're looking at some k subset of them, and what is this now? You're summing up over all, like, so it's like a restricted expectation. So I'm looking at these k vectors, these k random vectors that correspond to the elements in T. For each one of them, now I'm taking a kind of expectation. So what I'm writing is that this is exactly equal to expectation where yeah, so let me write what's the expectation of sigma k summation I in T vi star, where what is the expectation where for every I in T, vi is sampled independently from new I. Right. So this is by definition just that. So just let's just see about it. So fix this T. Let's fix a T. Now what are we doing for every coordinate in T? We are choosing the vector vi with some probability. But what is the weight? So what is, just look at any one particular assignment f. What is the weight that assignment f gets? It's exactly the probability of choosing those vectors from the corresponding ith coordinate.
Piyush, shouldn't, like, since your distribution is dependent on T, shouldn't the sum be outside?
No, it's not outside, it's inside. Why should it be outside? So just look at this, right? Your T is fixed, don't even worry about it. T is some fixed thing right now. Okay, we have one random variable for each coordinate, each element of T. Okay, that random variable is distributed in omega I, right? And what are we doing? So yeah, it's just formal equality. Just check, right? Suppose I choose. So how do I choose, right? So for each I have to go and choose a particular vector, which is the fi vector. Okay, I write down all these things. I get sigma I this. But what is the weight of just this choice that I just made? that weight is exactly this term here.
No. Yeah. It was
And so
simple. Yeah.
Okay. So nice. So the point is that the coefficient. So the coefficient. Oh well, okay, sorry. So I might have messed up a little bit. So okay. So what was this? So so we wrote this out, and so then yeah. So this is the so for a particular t, yes, we're right. So the coefficient of zi I and t is exactly the expectation. So okay, so this is not the full story. So there's also something else. So I forgot including something, which is this x to the n minus k. So this also is there. Is exactly e to the power expectation of sigma k summation I in t vi star when and since so I can just say that this is all just all of them, right? So I can just sample all of them, just ignore the things that are outside t. That doesn't change anything. Okay, so substitute in the first expression that we had. So in the expression, this one here. The expression star. We get that this that this whole thing so this we know that this was equal to all, so you have to go over all subsets S of yeah, so what was it? So M choose K. This is the same notation. Okay. Testing here. And this is just now S subset of M x to the yeah, x to the n minus the size of S minus 1 to the power S. And then we have the expectation of nu1 to nu m sampled according to nu, sorry, v1 to vm sampled according to nu. And then we are looking at sigma k of summation I in S vi transpose. Okay. But in particular, so of course these terms will vanish if k is bigger than m, right? So yeah, so only, I mean, so the so what is this k? K is the size of S. True size of S bigger than n or 0, right? Because there's no determinant there. So rearranging, this becomes summation k going from 0 to n, x to the n minus k minus 1 to the power k, summation all S subset of k size subsets of m of the expectation v1 to vn v sigma k summation I in S vi. Okay. Which is just the so I can now, by linearity of expectation, I can take it out. Summation k going from 0 to n, x to the n minus k minus 1 to the k S subset of sigma k INS. But what is this? Now let's sorry for the gone over time, but let's finish this. So now we apply our favorite lemma 3 again. Determinant of xi minus summation zi wi when the wi is the rank 1 matrix is exact, and let's just now put zi equal to 1, is exactly given by this summation where you sum over k size subsets of m sigma k of the summation of the corresponding to vi's. So this is exactly characteristic polynomial. The determinant of xi minus summation vi star. Okay, by exercise 3, which is exactly the expected characteristic polynomial. So this concludes it. Okay, so we'll just recap this again in the next class. And if there are any questions, take them now.
So this finishes the full proof, like that's it, right? All
Yes,
the components.
yes, all of